Welcome everyone for the lecture on components of powertrain. Today we are going to discuss one of the most important building blocks of electric vehicles, the EV powertrain. When we say powertrain, we are essentially talking about how energy flows inside an EV, how it gets converted, and how it finally moves the wheels. The fundamental working concept of a EV powertrain is based on generating torque through electromagnetic interactions. Instead of burning fuel to produce heat and pressure and torque, as in the case of internal combustion engines, in a traditional petrol or diesel car, the powertrain starts from the engine, then goes to the clutch, the gearbox, the drive shaft, and finally the wheels. But in an electric vehicle, the architecture changes completely. There is no engine, no combustion, no fuel, and in many cases even the gearbox becomes extremely simple. So the EV powertrain represents an entirely new way of converting stored electrical energy into motion. First, let us define the EV powertrain. In simple terms, the EV powertrain is the entire chain of components that store electrical energy, convert it into mechanical energy, and deliver that mechanical energy to the wheels. So the energy flow in an EV can be visualized in three major stages. The first one is an energy storage stage, where the battery stores DC electrical energy. The second one is energy conversion stage, where the power electronics devices and topologies convert DC power to AC power and controls the voltage, current, and frequency to operate the electric motor. The third one is the energy delivery stage, where the electric motor produces torque, which is transmitted through the driveline to the wheels. One key thing to remember is that electrical to mechanical conversion is highly efficient, typically 85%, 95%, whereas the internal combustion engines usually operate around 30%, 35% efficiency. This is a major reason why EVs consume less energy and offer lower running cost. The advantages of the EV systems over the traditional IC engine systems are: the EVs are able to achieve instant torque, high efficiency, and silent operation. In EV, there is no need for combustion cycles, turbochargers, cooling jackets, or exhaust systems. The EV powertrain is simpler, cleaner, and more efficient than IC engine systems. Now let's enter the first major component, the battery pack. The battery is the heart of an EV. It stores electrical energy in the form of chemical energy. Lithium-ion batteries are most commonly used because they offer high energy density, long cycle life, and relatively lower weight. The battery pack includes the cells, which are the basic chemical energy units, the modules, which are a group of cells arranged electrically and mechanically, the pack, which are multiple modules with cooling plates, casing, sensors, and a battery management system, which we call as BMS. The BMS is the brain of the battery system. The BMS plays a critical role. It monitors the voltage, temperature, and current of every cell. It performs cell balancing, protects the battery from overcharge, over-discharge, overheating, and even predicts remaining charge and life of the battery. Without the BMS, a lithium-ion battery would become unsafe. EV batteries heat up quickly during fast charging and high power acceleration. So the EV battery packs also include cooling systems, either air cooling or liquid cooling. Finally, the battery provides a constant DC output, but the load requirements of the motor keep changing. And that is where power electronics step in. The next important section of the powertrain is the power electronics subsystem. This includes three main components: the DC-DC converter. This converts the high voltage battery supply, for example, 300 to 800 V, into a lower voltage supply, 12 to 48 V, for auxiliary systems like lights, entertainment systems, and sensors. The onboard charger, OBC. This takes the AC power from the charging station and converts it to DC to charge the battery. The inverter. This is the most critical power electronic component in the EV powertrain. It converts DC power from the battery into AC power required by the electric motor, but it does much more than just conversion. It also controls the motor speed, motor torque, power delivery, regenerative braking behavior through pulse width modulation, PWM. The inverter adjusts voltage and frequency to meet the torque and speed requirements of the vehicle. The motor controller is sometimes integrated with the inverter. It receives signals from the accelerator pedal, the BMS, and vehicle control unit, and decides how much torque the motor should produce. It additionally optimizes the input parameters to manage efficiency and also protects the components at extreme conditions. Power electronics are the reason EVs are so smooth, responsive, and energy efficient. They manage the entire energy flow with high precision. Now let's come to the component that produces motion, the electric motor. EVs mainly use three types of motors: permanent magnet synchronous motor, PMSM, induction motor, IM, switched reluctance motor, SRM. PMSM motors are the most widely used today because they provide high efficiency, high torque density, and excellent speed control. Most modern EVs, including Tesla, Tata, Hyundai, and MG, use permanent magnet synchronous motors. Induction motors, originally used by Tesla Model S and X, do not require magnets and are robust and reliable, but slightly less efficient compared to PMSM. Switched reluctance motors are cheaper and rugged, but produce torque, ripple, and noise. They are improving, but not yet mainstream in passenger EVs. Let's discuss on the principle of operation of a motor. The motor operates based on electromagnetic fields. When AC current flows through the stator windings, a rotating magnetic field is generated. This interacts with the rotor, producing torque. Unlike IC engines, which need multiple revolutions to produce power efficiently, electric motors produce high torque even at 0 RPM. This is why EVs accelerate so quickly. Another unique feature is regenerative braking. During braking, the motor becomes a generator, converting kinetic energy back into electrical energy and charging the battery. This increases the driving range and reduces the brake shoe wear and increases the brake shoe life. Finally, we shall discuss on the transmission systems. Transmission systems are basically classified into single transmission, multi-transmission, and continuously variable transmission. Single gear transmission system has fixed gear, and so they have a single gear ratio, and this ratio is carefully designed and optimized of the electric motor performance characteristics. In an EV, the motor can generate usable torque across a broad RPM range. That's why most EVs use a single-speed transmission. Additionally, the fixed gear system plays a major role in effective regenerative braking. The single-speed transmission driveline may include a reduction gearbox, simple gear set, and a differential for front-wheel or rear-wheel drive. A car's differential allows the drive wheels to rotate at different speeds, essential for smooth turning as the outer wheel travels a greater distance than the inner wheel. Because torque delivery is immediate and smooth, the transmission system becomes much simpler and lighter. This reduces maintenance and improves reliability. Some high-performance EVs use two-speed gearboxes. For example, Porsche Taycan uses a two-speed transmission on the rear axle to balance acceleration and top speed efficiency. But for most EVs, a single-speed reduction gear is sufficient. Multi-speed transmission system provides the ability to change between several gear ratios. Components of a multi-gear transmission system is the electric motor, the multiple gears, and the clutches. During multiple gear shifting, clutches help to engage or disengage one gear while selecting the other gear. The principle of a multi-gear system is lower gears ratios provide higher torque and acceleration, while higher gear ratio provides speed and efficiency. CVT provides an infinite number of gear ratio within a specified range. Components of the CVT are the input shaft, the variable diameter pulleys, the metal chain, and the transmission control system. We will now see how the variable diameter pulley works to achieve an infinite gear ratio within a specified range. When one pulley increases its diameter relatively, the other pulley reduces its diameter to achieve a transition from one gear ratio to another gear ratio. In CVT, the transition is continuous and smooth and not discrete and discontinuous, as in the case of a multi-gear system. These are the real-time examples of the car that use the different types of transmission system. Chevrolet Bolt EV and Nissan Leaf have single gear system. Tesla Model S is provided with a multi-gear system, and Toyota Prius Prime and Honda Clarity Electric have CVT technology implemented in them. Let us quickly summarize the energy flow through the EV powertrain. Electrical energy stored in the battery pack flows to the power electronics. The inverter converts DC into AC and controls motor torque. The electric motor converts electrical energy into mechanical rotational power. The reduction gearbox and differential transfer torque to the wheels. During braking, the motor works in reverse, sending energy back to the battery through regenerative braking. This entire system results in quiet, efficient, and responsive vehicle motion. The EV powertrains are simpler than combustion vehicles, but rely heavily on electrical and electronic precision. Finally, the consolidated pillars of EV technology are the electromagnetics, the BMS, the power electronic systems, and the simplified driveline. The future challenges are thermal management and the control algorithms. That concludes our first lecture on the fundamental concepts and components of an EV powertrain. You should now have a clear picture of how an EV stores energy, how it converts it, and how it finally produces motion. Understanding this is the first step in mastering EV engineering. Thank you, and we shall meet again in another topic on EV powertrains in the next video.